Sorry, so something changed on the screen. I see myself. Okay. So yeah, it's a pleasure to introduce Professor Fabris-Rotelli. Though I must say that introducing somebody I've never met before is a bit odd, but anyway, I wish we could have met in person, but that's not happening. So thanks a lot for agreeing to give this talk. Professor Fabris-Rotelli did a PhD in applied mathematics from the University of Pretoria. Her research interests are in image analysis, spatial statistics, machine learning, and I guess that's what she will be using, I guess, to talk about a problem that I'm sure all of us in India must have faced in the past, that roads which are not marked on the map, and then what do? And I had this situation where Google showed something, and when I go, the road does not exist, or vice versa. And so she'll be talking about informal road detection, neural network for society impact. Thanks.
Thank you very much. I really appreciate it. You can hear me properly.
Yes. Yes.
Awesome. Thank you. All right. Yeah. Thank you. Thank you very much for having me here. I'm really excited to be talking to everyone today. And I'm particularly excited today because I'm talking to BRICS countries. This is a project that we've been working on, and as it goes along, you'll realize why it's nice to have this audience specifically. So this is not a work all by myself. I have a team with me. So Renata, Gao, Pravesh, and Victoria, and a number of other postgrad students as well. So Renata and Gao are in the Department of Statistics with me at the University of Pretoria. Pravesh Deba is at the CSR in Pretoria, South Africa. And then we have a further collaborator, Victoria, who's from our Department of Geography, apologies for the spelling there, Geoinformatics and Meteorology, also at the University of Pretoria. This project was sponsored by Data Science Africa, and I'll go into a little bit more about how we got that money just now as well. Slides, not going down, oops. Okay, there. Right, so just a little bit about spatial data. This is a mathematics conference, so it's not always, not everyone always knows a lot about spatial analysis. Yes, so I am an applied mathematician, but I've been in the Department of Statistics as a staff member while I was completing my studies as well. And I've sort of merged into spatial statistics because I did image processing in applied mathematics. So remote sensing and all of that falls very nicely as a sort of in-between field. So not only remote sensing, I do a lot of spatial methodology development as well. So the big thing about spatial data is it is big. And there's a really nice paper here if anyone's interested in something about geospatial data. It's a review paper. It's not very new anymore, but 2016 is not too long ago. And it's a review of what's happening in spatial data and where is research really, really needed that's going to make it possible for us to do really good geospatial research into the future. And the big thing that comes out of here is that, first of all, geospatial data acquisition is now easy. 10 years ago, we didn't have maybe 10 years is a bit too short, but not too long ago, we didn't have access to as much spatial data as we do now. Now we have GPS off all our phones. Most of us have smartphones and it's tracking you constantly. All the apps are tracking you. Insurers are tracking you. So there's a lot of spatial data available now that wasn't there in the past. So there's actually so much that we haven't yet got the expertise to really deal with this. So it's a really exciting field. The next thing is that spatial data is really a big data problem. So there's big data and then there's spatial data. And the reason is that we've got traditional statistical data. We'll have a database, we'll have rows as your observation and your variables in the columns. But the thing with spatial data is you've then got a location attached to it, and you can also have time attached to it. So it can be spatial, but also spatio-temporal. And the big difference between traditional statistical analysis and spatial analysis is that spatial data is dependent in space, and if you have time, in time. Whereas normally we assume all our observations to be IID, and that simplifies a lot. And what this means is that we need to compare every pair of observations when we're doing spatial analysis. How far apart are they in space? How far apart are they in time? So if you've got n observations, you end up with n squared comparisons. And I think we all know how to do calculations, and that is big. So spatial data is really truly a big data problem. You need to be clever about how you do your code. You need to be clever about how you render spatial maps, etc. But once you've got big data, and we've got this big spatial data, the research that we do will really provide opportunities for societal management and decision making, enormous opportunities. And this paper really covers that a lot. It covers a lot also about how do you even store spatial data and access it easy. These are really big data sets. So spatial data is really exciting. Spatial statistics is really exciting, and this is where our project began. So as we all know, everyone listening to me, is that informal settlements are present in many of our developing countries in the global south, and I say south, but obviously a lot of you are north as well, but developing countries. And these pose severe challenges for sustainable development, service delivery, and crisis management. And Renata and I published a chapter in a book last year in response to the COVID-19 pandemic about this sort of issue. If we don't know where our roads are, how are we going to service the people that live in this area in terms of, for example, ambulances? Maybe we need to get to them, their phone, they have severe COVID reaction, they need to be hospitalized, and the ambulances can't even find them. If you go a step further, these people now want to get vaccinated. How do they get to a vaccination station? How do you position your vaccination stations if you don't know how people are going to travel? So you don't know where the roads are. So these are very current examples that I'm listing, but obviously we all know that there's, in general society, really a need to know where roads are. First issue, of course, being how to get somewhere, even if it's not an emergency. So we refer to informal roads as any roads created by residents without government approval. So roads that have appeared out of convenience from people in a community. They may be formal, traditional, or informal. But the key being that they're not on the maps. So if you go use an app, they're generally not there. And they arise naturally by human movement on foot or by vehicle. But the government doesn't maintain them. They were not authorized by government, and they're not on any commonly recorded official databases or online maps. There is a project called OpenStreetMaps that has community sort of tracking roads and putting them in, but it's not maintained or checked by government as a follow-on step. So it's very much a crowdsourced type of thing. So that is available, and that's a really, really good project. But we wanted more than that. We wanted to be able to give an algorithm that could take a remote sensing image and detect these roads. So the challenges that occur with this, and we all will be very aware of this, is that these informal roads occur in irregular networks. They don't have clear boundaries or center lines. Roads that are built by government and maintained by government have a set with these regulations in place. So when you do image recognition or image detection, those roads have set properties that you can teach the algorithm. Informal roads are irregular. Okay, they're also usually unpaved, meaning they are heterogeneous in color. So they don't have this natural tar color. They fade into the surroundings. So where does the road end and the pavement begin, or the backyard begin? Those sort of complications. And of course, as what I've just said, they contradict assumptions made by traditional formal road extraction methods. So here's some examples. So this is from various places in South Africa. So here's an example where it's quite clear that this is pure convenience. I mean, surely a road should have gone straight through there, but it's more convenient to drive there or there. There's an island in the middle. Do people drive over it? Will it maybe have a road in the end? We're also interested not just in roads, but in the paths between our slums or our shacks. Here there's a road. Where does it go? Is this now a road, or is this a backyard? Here's an example of maybe a road that's either beginning or it's not used anymore, but you don't know. But can we pick that up as a possibility? Maybe this one is the one that's been used more commonly now. Yeah, again, paths between shacks. We're particularly interested in this sort of thing as well. I work with a criminologist from our geography department, and we have crime data for Khayelitsha in South Africa. And we would like to be able to sort of figure out spatially what's happening with crime. Where can people move? Is that why there's crime here? Is it easy to move? Is it easy to hide, etc.? This is an example of the variable width. So here it seems like it's quite clearly a road, but then what happens here? Is it still a road, or is it just a pathway? What happens? Here's an example of the surface changing. Here it sort of seems like it might be tar, but then it becomes sand. Questionable. Here you've got a different area with different sand colors, and here, as a human, because we're very good at pattern recognition, we would be able to sort of determine that there's possibly a road here and it sort of goes there. But how do you train an algorithm to learn that sort of information? Here as well, this seems to be a road, but where's the road? Which is backyard, which is pavement? Same there. Here, even now you've got vegetation causing more issues. In this example, we have a tree going over the road, and your algorithm needs to learn that a tree can hang over a road. That doesn't mean that you can't drive on it, so it should be connected, still remain a road. You also have shadows that could cause issues. And then here, this is a sort of a field, but should it be road? It's very complicated. And what you'll see everywhere is that the surface is usually sand, but there's sand also in backyard, so you can't use spectral signature and remote sensing to necessarily pick these out very easily. You really need more information. So we really struggled with this work in the beginning. So Renata Tide, she's now my PhD student in her second year. She started with this work in her honors and her masters. So she's now in her fifth year working on this sort of direction. And we got her paper from her honors and masters published in 2019 in the South African Geographical Journal, which is quite a good geographical journal in South Africa. But we actually sent it to 4 international journals before that. And we became incredibly despondent, not because, you get a bad review and that's fine. You can accept that. You can always write better. Nothing, can't moan about that. But the comments were always so short-sighted. They were always, all the reviewers kept saying, but why would a government allow an informal road to appear? How can they allow that sort of thing to happen? Why would this be happening? And we just thought, sure, this is really, the developed world doesn't understand why these roads are here and why there's a need for this. And then when we submitted it to a South African journal, they immediately accepted it. We had some edits to do and it was in. And then we realized that this is really a concept that is not understood internationally. We also got some valuable comments from these reviewers, and a few of them said, well, why don't you just use a neural net for such an algorithm? Because there are neural network road detection algorithms that exist in remote sensing. The issue is that you need for neural nets data, and there is no data set of informal roads, image data that are labeled images. So we couldn't do that. And it's vastly different from formal roads, as I've indicated to you already. So this was very problematic. So in Renata's honors and masters, she developed a non-neural net based algorithm, purely morphology based, sort of figuring out learning about the shapes of the roads and if there are long structures and trying to pick them out. So that was a step towards a good algorithm. It wasn't perfect. So we knew we could still improve on it. So this paper was really about the uncertainty. What makes informal roads so uncertain? In other words, how do we know that road is there compared to a formal road? And we sort of had a little bit of a philosophical discussion in this paper. So as I've just said, the limitation is training data. The only other paper, and I can be corrected, but we could not find anything that looks at informal roads, is this paper by Nabrigo et al. So these 2 papers are the only ones that actually think about this concept of an informal road that we've come across. There are many papers on road extraction algorithms, but not focusing on the nuances of informal roads in our developing countries. So we thought, right, we need to do something. And then I saw a call for Data Science Africa funding. And I applied for the grant, and we got it. So we applied for this in August 2020. There's only 10 PIs that are awarded the funding. So we got some funding, and the aim of the project was to develop a ground truth training set of informal roads in South Africa. And once we have it, to make it freely available for others to also use this data set. Then with that, now we have a good training set, train a neural network on informal roads, which is not available anywhere. And this would obviously be useful not just for South Africa, but anywhere in Africa and other developing countries across the world. And really, we're specifically very interested in these between the shacks type of movements. And that's very complicated because it's you need very high res imagery. Furthermore, our aim was to do capacity development in GIS with statistics skills. So there's, I think as we'll all know, not many of us do maths and stats and then learn spatial GIS or any geography skills on the side. They're traditionally not sort of in the same departments or work together. But there's a big need in GIS for mathematical and statistical skills to add to the software, to make new algorithms that are more powerful. As this data gets bigger and bigger, that we have to be cleverer. So really exciting field to be in. So in our project, we've got the team, and then we also have some postgrad students to work on capacity development. So we did a data set collection, and I say it sounds really easy, data set collection, but actually it was a digitization, manual digitization that they did of images for honor students now in this year, 2021. And then we have a master student who started 2021 and will finish next year in 2022, also on the team. So he's responsible for once we've got the labeled data set, to build the model with a neural net. So this is our team. There's myself, so I'm in spatial statistics and image processing. Renata is my PhD student and also a lecturer in our department. Dr. Khal Maribe is a senior lecturer in our department, and his expertise are statistics and machine learning. So he's the expert in the neural net side of things here. Professor Pravesh Deba is a statistics and remote sensing expert. He completed his PhD in spatial stats from the University of Twente, Netherlands. Dr. Victoria Rautenbach is a GIS expert. And then we've got 4 honor students. I'm very proud to say all female and master students. So our genders here are 7 females and 3 males. So we feel quite good about that. Not to say that males are not welcome on the team, of course. And then in 2022, we're going to put some additional honor students on this project, and I'll add to that at the end of the talk. So our honor students, that's our 4th year students basically, did the digitizing in their honors year. They have to do like a mini research project. So this was part of their project. And this is the Khayelitsha. This sort of, I'll show you now on a map on the next slide as well. This is Khayelitsha in Cape Town in South Africa. This is aerial photography. And we were very lucky. You'll see it's very high res, it's 30 centimeters resolution. In the budget for Data Science Africa, I actually asked for money to buy imagery. Remote sensing imagery can be very expensive. We couldn't work with low res imagery. Even 1 meter was too high because those gaps between shacks will often be ½ a meter, and we can't label them if we can't see properly. So I budgeted for buying remote sensing imagery, only to find that my budget was way too little. So one of these images, for example, and won't even cover this whole area here, would cost, say, $1,000 US dollars. If you found an image without cloud, and that's, the clearer it is, the more expensive it gets. But then after some search, and because I have these connections with our geography department, that they know where all the data is, we realized that the city of Cape Town, the government, actually has aerial photography of Cape Town at this high res, 30 centimeters, and it was freely available. So this was really, really good news. We could use it to digitize. You can pull it into ArcGIS and digitize them and export it and do your analysis in Python or R or wherever you need. So the little purple bits are the areas that we digitize. We didn't do the whole of Khayelitsha, and I will show you now why. So this is the Cape Town, and there's the Cape Point, and Khayelitsha is this red bit. So the extent of Khayelitsha is something that gets redefined quite regularly, but this bit here is Khayelitsha, what we are focusing on. So there are also informal settlements across there, but we just focus on here because we're just trying to develop a labeled data set. So what's interesting about Khayelitsha, so this image is somewhere there. There's the highway up there, the N2 highway. And this image I'm going to show you on the next slide is over there. So what's interesting about Khayelitsha is Khayelitsha was actually what we call formal settlements. In other words, back in the apartheid days, people were forced to go settle there. They were put there. It was set up as a formal settlement. They were given little matchbox houses. You can see that here the streets are very regular. And if you looked on Google Maps with some of the high-res imagery, you'll see that all these stands are very standard size. And the roads are easy. They're named, first of all, so the government knows about them. So this is not the area that we were interested in. But on the outskirts of Khayelitsha, these areas, which you can immediately see the different pattern, this is all shacks, and this is real informal settlements. So there's so many people in Khayelitsha that people are settled on the outskirts. So these purple bits are all the little polygons that we selected that have these shacks in them. So the rest is quite formal, but we're interested in the roads that develop in these areas. Right, so we had 23 of those purple polygons. The 4 students digitized all of them. So we had a repetition of 4 for every single polygon. We discussed in length the rules for digitizing. So when you open ArcGIS, you have to set your resolution at a certain level. That what you're viewing, obviously not the image resolution stays it is, but what you're viewing it on your computer, and you digitize there. We digitized polygons, so roads as polygons, not as lines, the center line. So a lot of some road detection techniques, formal road detection techniques, will just work on the center line because roads are all the same width. It's very regular. But here, of course, we know that that's not the case. So we really wanted to have the full extent. So if the road was wider here and then thinner, then we captured it, all of it. So it set rules. We met every single week for the whole year for an hour. And if there was anything that students were confused about, we made new rules and we made sure everyone was on the same path. We did with Polygon 11, we chose that one because it was quite large. We did that one as a sort of pilot. So the first one to sort of see how everyone would figure out how to do it. These 4 honor students had never used GIS software before, so they had to learn the software and how to digitize and think about the rules and that sort of thing. So it was really nice to see how they grew and learned. And then we used that as the pilot one, and we fitted a model so long on that polygon. And then at the end, they went back and redid that one, acknowledging that the first one would have been a bit fuzzy. Then we looked at the accuracy of the group. So the 4 different digitizers, how well did they correlate with each other? Where were the issues? What were the things that were difficult? And then we merged the digitization to get a final labeled data set. So we sort of had some variance among the 4 students, but they where it agreed most became the final digitization. And then we will shortly have available all the shape files so that anyone can download it and train their own neural net. That will happen beginning of January. We're just making it pretty. Right, and then once you've got a digitization, how do you decide that it's a good digitization? And they use in GIS evaluation metrics, as we do across maths and stats. For example, completeness. So how much did we capture everything that should be a road pixel? Then there's things called logical consistency. So how well did the rules for the data capturing process, were they followed? Okay, so pure logic. Positional accuracy. So how closely does the digitized data object match the spatial position of its real life counterpart? Does it make sense? And then there are others. So they obviously covered a whole bunch of them, and there are many available. There's also the difference between using pixel-based and object-based. So pixel-based, you look at each pixel, you compare it to the others, and you say, okay, is this pixel the same as all the others? Whereas object-based first extracts object from an image, and then detects how well that object has been detected. And that's quite difficult to do because you have to have an object detection method first, or some sort of extraction method, or you must have done your digitization in an object-based way. So we do have polygons, so we could do that. But we did also try and, well, we labeled different types of roads. We have the roads, we have the paths between the shacks, we have footpaths through fields, and then we have another category which is called uncertain. But of course, there's a lot of sort of overlap between these types as well. So we definitely could still look at that. So the one thing that we have used, and I'll show you that I have used some other measures as well, but this one is sort of the most interesting for me, and I thought I'd share it with you today, is what we call the V measure. So it was done by Nowasad and Stepinski not too long ago. And it's actually a harmonic mean. There you see that formula. And H and C are what we call homogeneity. They're both homogeneity measures. This one actually stands for completeness and this one for homogeneity, but you can see they're actually similar in the same way. So they both have this formula. The only difference is you flip them, you do it opposite. So let me just explain the notation now. So you've got A is your whole region. Okay, so for example, the square. AJ is then one of the regions in here. And then you've got a variance of the regions in AJ versus the variance of the regions over all of them. So the C value is the homogeneity of the partition, right, into versus the whole domain, right? So this orange bit. Whereas the H is the other way around. So you flip the idea of, so these, for example, you can see these irregular boundaries could be the digitization that we did on the maps. And then you flip it the other way and you see how well does the original or the true correspond with that. Now, the big thing with all these measures here, evaluation metrics, is that traditionally you have a ground truth and then you're checking yours versus it. Now, we have no ground truth. We've got 4 digitizers who are all non-ground truth. And we actually want to check how well do they correspond to each other. So what we did is we compared each of the students to all of the other students and all comparisons so that you can sort of get a internal consistency type of measure. So this is quite a powerful formula. The variance is calculated, I haven't included here, but you can see it in the paper. This variance is calculated using entropy measures, but the bottom and the top. So it really takes into account a lot of information. And it's a value between 0 and 1. 0 means these two things have nothing in common. They're far too different. And 1 means it's a perfect replica. So these match exactly. So obviously you want a high V beta value. And what's really nice is there's a package in R called Sabre that calculates this for you. It's not too difficult to calculate yourself, but you know, if there's something that's already there, it's always very nice. So once the 4 students have digitized their data, we want to be able to say this is a good enough data set that can be used. So this is a comparison of the V measure, so that V beta, for the 4 students. So you can see there's student 1, 2, 3, and 4, and again here 1, 2, 3, 4. So for example, this one is the V measure for student 1 versus student 4. And these each bar is one of the polygons. Remember, there were 23 polygons. You'll notice that polygon 3 is missing everywhere. And that is because when we look closely up at it, there were actually no rows of anything that was worth digitizing. So we've left it on purpose because it's, you know, we made a decision that it wasn't something that needed to be considered. But obviously it won't be in the digitized data set. And obviously you can see the range goes from 0 to 1, and we want high value. So it's not too bad, but you can see that some polygons often have low values, like polygon 1 seems to always be relatively low. And that gives you an indication of which polygons were maybe very complex and were difficult to digitize, and we should go look at again and try and improve. And then one of the honor students made this beautiful flower picture. It's the same thing that you're looking at, it's just represented in another way. So student 1 versus student 2, these are the polygons again, the V measures, but now they're ordered in order of smallest to highest. So you can see the polygon 9 is often quite high. So that one is relatively easy, but 1, 21, 20, 19, 1 and 19, 19 and 1, 1 and 20, these seem to be have been quite difficult to digitize. So that's a nice graphic. This is done in R ggplot with a few extra lines of code, but really, really nice stuff that you can do in R ggplot. Here's an example of what it would look like. So you've got the 4 different colors. They've been layered on in a transparent manner. 1, 2, 3, and 4. And you can see some places they sort of overlap a lot. Yeah, for example, and then you get to this sort of area, and this area was actually so this is all shacks here, and this is sort of in a field alongside it, and it's sort of still developing. And there were only a few houses here, but it was quite clear that there's little footpaths, the yellow, through the field from this area across this sort of road that appears here. And then the extent of these roads here varied enormously. And obviously it became human intuition as to how wide you should do it. So you can see the difference in human pattern recognition happening here. Here they overlap quite nicely because there's shacks, so it's quite visible. There's a roof, it can't be a road, but there should definitely be a road between. But you can see some of the students found little pathways between them even, and some didn't pick that up. So this is just an example of how complex this digitization was, but we did it. So we've got a beautiful data set that looks like this. So this is the combined data set, but the one that we will publish for people to use will be the merged with just one layer. Okay, so while we were developing this digitized data set during the year, the master's student conducted a literature review of existing road detection methods using neural nets to find the best one available for formal roads currently. And then we want to see if we can now use that existing architecture on our digitized data set, and will it improve? Or can we then also tweak the architecture further? So there were a number of models that were determined as best for road detection. There's a really nice algorithm paper published last year, a state-of-the-art review. Always nice to find a paper like that. And what was really nice about this paper is that they didn't just list all the architectures available. They actually went and implemented all of them and actually have measures, F1 scores of how well they worked, so that you can really take the best ones. So there were top 3 that we chose from there to implement it. Thus far, we've trained the GANS UNET model, which is one of those 3, which is from this reference. Right, so for this GANS UNET model, we had 64 tiles of 600 by 600 pixels. We only use polygon 11 for the results I'm going to show you now, so it's not even the full training data set. And then, so you've got the original tiles from that Cape Town imagery, the corresponding digitized segmentation, so ours, only for polygon 11. And then we also added in the city of Cape Town roads, so the existing formal roads, because otherwise, obviously, you will train it to think that that's not a road. So we added in existing formal roads, of our informal roads on top of it. And then once we trained it, we looked at if you train it without our informal roads added and with it to see what the difference is. We used 70% training, 15% validation, and 50% testing. We also did artificial enlargement by flipping, cropping, rotating, and translating, so that we ended up with a total of 206 images for training. These, remember, are 30 centimeter resolution. It was run on a Linode Cloud GPU. We used a batch size of 64, learning rate of 0.02, which was reduced as we went along, and some other details there. And the code is available. This is not our code. That's from this article. So it is freely available, which is really nice to run this, obviously without tweaks. Okay, so here's some results. So this is the original imagery, for example. This is the model one is the without us adding the informal roads into the training data. And this is with the informal roads added in. The labels is the training data that we gave it. So the original plus the labels. And you can see immediately that we definitely pick up more roads than the output of without the informal roads, which is really promising. So it's not perfectly there yet. There's things that we'd maybe like to be able to pick out, for example, here within the shacks, that sort of thing. But the data set still needs to be go through another level of cleaning, and I think fresh eyes as well. But really positive that the data set is really usable to improve upon this. All right, so what's next? So we've trained that UNET GANS model, so we want to look at the other models. We haven't tweaked it at all. We left the architecture exactly as is. We've got that in a draft paper form that we're going to submit next week to a journal. We also want to look at training for different road types. So in this work here, we just put all the road types together. So we haven't, so the black, apologies, is City of Cape Town roads, and the gray is our informal roads. But we haven't you'll see differentiated between road types, so road versus walkway or between shacks type of thing. So we'd like to do that. So it's not just a road or not road, it's a what road are you seeing? Do these evaluation measures work? Are they suitable for informal roads, or is there something that we need to take into account, nuances about informal roads that are not used in traditional evaluation measures because this has never been considered before? We also want to do some further digitizing in 2022 with some new honors students. We're going to pull in some GIS students as well so that they can see the the statistics side of things, and our statistics students can see the GIS side of things. We're really trying to go very transdisciplinary. And then there's also the question about different soil types. So Khayelitsha is near the coast, so it's very beachy type of soil. But if you came up to Gauteng, where I stay, you get sort of a clayey red soil. So what will happen if I now go and plug in an image from Gauteng into this model that was trained on Khayelitsha type of sand? So maybe we need to add data into our training data set. The city of Tshwane, Pretoria in Gauteng also has imagery, aerial imagery that we could use at a high res. We could digitize that. And then another very interesting question is, once you know about these roads, it would be really important for society to be able to know what the quality of that road is. I think we've all driven down a road and gone, oh my gosh, should not have driven, this road was a bad idea, I should have taken the long route, you know? And this is something that could be quite valuable. We have so while we're digitizing, we've got high res, we could do sort of an indication of that. And then you could get this information also trained within the model. And really important is looking into neural net explainability. So why does the neural net predict it's this road type? What are the elements within a neural net that are pulling this out? So how do we really differentiate informal roads? Right, so just a little bit more on my group's research. So we do a lot in spatial stats. It's not only this road network development that we're working on, general spatial stats methodology development, a lot of crime data that I'm working on. I've got a PhD student specifically working on crime in relation to roads. So are they correlated? Also weather and crime, but spatially. I've got a large team working on COVID-19 modeling, specifically spatial COVID-19 modeling. And this is really essential because this virus spreads spatially. And if you don't do a spatial model, you're not going to capture all the nuances of the disease spread. So we've got a few papers on that. If anyone's interested in, you're welcome to pop me an email and I'll share some links with you. Yeah, and we do a lot of point patterns and road networks as well. Thank you. I think my time was okay. There's my email address if anybody has any questions or wants to chat afterwards. I'm not sure if the room is muted. I can't hear anything. Thanks. I see some hand clapping there in the chat. Yeah, see, yeah, the main room, I can see them, but their camera's on, but seems like they've gone offline. I'll open it to anyone in the chat if they'd like to ask a question. You can even just type it in the chat. Otherwise, I'll close. The system is hung. Okay. Maybe just give them enough time. See, there's a question here. Paolo, did you even try to bother to explain to the reviewers the needs? Yes, Paolo. So we tried. Sometimes one or two of them gave us a major revision, and then we would, do a big rebuttal. And they were just really not interested in it. It was very disappointing. I felt quite sorry for Renata, my student, because she was a junior postgrad student. It's very disheartening to be rejected so often. But yeah, so we did try, but it wasn't well received. So indeed. I don't know, maybe it's a nice point to discuss. I don't know. I've always felt like we get a little bit of bias against, and I'm sure maybe the other BRICS countries can maybe comment as well. But I really feel as soon as they see that you're from Africa or wherever, that you get a little bit bias against you, that it can't possibly be good research. Maybe it's as a more junior researcher, you still have to build your name, but yeah, it was quite frustrating. But it's better now. Nick says, thanks for the talk. Could your approach be extended to identifying game trails? Oh, yes, Nick, so we actually had this, who commented on this? I can't remember. I've actually had that question before. So I think absolutely, if we can do the parts between in the fields, then it can do exactly that as well. Absolutely. We're back. Main room is back. Can't hear. Can you hear them? I can't hear them. Your sound's not on.
Can you hear me now?
Yes, I can hear you. Technology, so complicated.
Okay. No, so it turned out that the host, the system from which it was hosted, that hung up. And if we had closed that down, then of course the meeting would have shut down. So,
yeah.
So we had to log in from the other machine, and sorry about that.
Oh dear. No, don't worry.
So I guess you hosted yourself. But,
and we had some questions in there. I don't know if there's more questions.
I guess you can hear me, but I can't hear you. Sorry.
I can hear you.
Hey, what happened?
Oh my gosh.
Okay.
Recording in progress.
Now there is an echo.
Hey, can you hear me?
Oh, so sad.
Now there's echo. I think the streaming is probably coming through that side as well. There. Yes, I can hear now.
I think we are back online. That's what it looks like. Yeah, okay. Sorry about this. Oh, wow.
I can hear. I have a
sorry, I think it's probably good to just because this hung up again for 2 minutes, and are we back online or not online? I'm actually not sure if I'm or not. So,
I can hear you guys.
oh, you can hear. Okay, good. Are there questions from the audience here? Okay, so I had a question, I guess, about the ground truth part of it. Have you thought about, I guess, in terms of usability, finally? You're labeled using 4 different people, and I guess cross-checking the 4 things is one way, but actually going to that area and checking what the roads are. And is that something that you've thought about? And
so we have thought about it, and actually, so Renata's one of her co-supervisors in her master's and a PhD, a master's and honors was Professor Alfred Stein from the University of Twente, and he also said the same thing. But I'm sure that many of you can appreciate that going into these areas is incredibly difficult, and there's a huge, vast area size. So no, but simply because of that, because I think it's not possible, and I think that you just need to do more quality checks on your data, maybe have more digitize it. I think that will be more effective than going into the area. The other complication as well is that imagery is 2017 imagery, and if you go and look now at imagery on Google, it looks vastly different. There's a lot of growth. So there is no, 2017 is 5 years ago. There's no more. There's no ground truth. That ground truth doesn't exist anymore. So that's a bit complicated. Yeah.
Yeah. Yeah, very, very nice work. Yeah. Any other? Just hold on. There's one more question.
Hello, nice talk. This great lecture.
I just have a question about like how effective this model would be for different terrains. For example, let's say a hilly terrain versus grassland or something like that. Have you taken that into account?
Yes, excellent question. So we haven't, and I think that's definitely the next step. So at the moment, it's trained for that sort of environment, and Kailicha has got its own characteristics. But I think if you'd have to grow the training, the labeled data set with areas that are also within more grassy, more trees. So Kailicha doesn't have a lot of trees. So maybe you go for areas with more grass, more trees, hills, all those sort of things. Absolutely. That needs to be added into the data set for sure. Nick, in your introduction, you mentioned GPS data from cell phones. I suppose there's no possibility of getting such data and incorporating. So Nick, in our COVID modeling, we got some cell phone data that was given via Vodacom to CSIR for the COVID-19 response, highly confidential. So it's almost impossible to get permission to use that, especially now with personal protection of information and all that sort of thing. So in fact, when you look at literature, there's a lot of people that, there's a lot of remote sensing research that uses cell phone data incorporated into it. But then you have to have access to this information. And I think it very much depends on the government's decision on your data belongs to the government and we can use it, or it's personal information. In South Africa, it's further complicated by the fact that we have a number of service providers and none of them hold a high enough percentage of the country's population to be representative. We actually did a paper on representative mobility for COVID-19 using cell phone data and stuff like Facebook data. So I think that there's a possibility, but I think it's not representative enough to use cell phone data.
Any other questions? Sorry, I think if there are questions on chat, you will have to read them because if you click on the chat, it hangs up again. So
no problem. There's no more questions there.
I think, okay, great. So I think there are no other questions. Thanks a lot for this great talk. It was very exciting work.
Thank you. Thanks for having me. Really, really exciting to be here.
Are we able to close the meeting now, or what's the... It's hanging again. Okay.